see my slides?
Yes.
Okay, great. Can I start?
Yes.
All right. Let me share the slides. Just a moment. All right. Good morning. So it is my great pleasure to present my work here on this conference. So today I'm going to talk about the Beetle antenna search for online model-free optimization. So Beetle antenna search is a new algorithm proposed by us a few years ago. Like this algorithm, actually, it is something like the particle swarm optimization, also like genetic algorithm, which is a purely data-driven model-free. But the difference for this Beetle antenna search is that it is really fast. You know, like PSO, particle swarm optimization, this is based on a swarm of particles. Because it is a swarm of particles, usually totally n particles. If n is pretty big, definitely your computational burden will be very high. Well, for Beetle antenna search, this is not a swarm algorithm. We only need a single beetle. Therefore, it is pretty fast. Well, actually, yeah, this algorithm is inspired by the foraging behavior of beetles. Let's look at this picture. Imagine that there is a beetle, as shown here. There is a piece of pizza placed in a room. Well, the beetle originally cannot see the pizza, but it can smell the pizza. Well, mathematically, we can imagine this problem in a different way. We have a piece of pizza, the smell of the pizza distributes, the smell concentration distributes in this space. Well, at different locations, we have different levels of the smell strength. If the position is very close to the pizza, definitely the smell is very strong. When it is far away from the pizza, the smell will be low. And in space, the smell generated by the pizza will be a function, right? This function has its maximum value at the location of the pizza. Well, what the beetle needs to do, because it cannot see the pizza, it needs to use its antenna to smell locally, which is kind of like take samplings from local space on the smell and gradually find a trace to approach to the pizza, which is the global optimal value. Well, if we look at the problem in this way, we can model the problem as an optimization problem, and we can get inspirations from that to design a beetle-inspired algorithm. That is what we call as Beetle antenna search, because basically it is based on the behaviors of the beetle antennas. Well, how does it work? Well, the mechanism is pretty simple. Look at the beetle at the beginning over here. There are two antennas, the left one and the right one. If the smell measured by the left antenna is higher than the right antenna, it will turn left. If reversely, if the right antenna gets a higher smell strength, meaning that the pizza must locate to the right direction, and therefore the beetle will turn to the right direction. And using this very simple rule, so the beetle will keep check the comparisons between the smell sampled by the antennas, the left antenna and the right antenna at different locations. And it will generate a trend to move towards the pizza, to move towards the global optimum, and finally localize the global optimum. Well, our algorithm is a generalization of this simple behavior from two-dimensional space to generally n-dimensional space. Well, we can model the system in this way. Okay, we have a beetle. we can treat the beetle as a circle, and there is a center, and on two sides of the center, there is a left antenna, there is a right antenna. We can define the distance between the two antennas as D0. We are going to use the parameter D0 later. And every time we just sample the value of the function to be optimized at the position of the left antenna and at the position of the right antenna, and make a comparison to see which one is bigger, which one is lower, and then determine where to go next step. So the updates rule is quite simple, as highlighted in over here. So first of all, we generate a random direction, which is a heading direction for the beetle in n-dimensional space, which is a random variable. We randomly determine the orientation of the beetle in the space, n-dimensional space. And then we do the normalization to make it is purely meaningful for only the direction. There is no meaning for the length of this vector. And then we define this one because, you know, the direction is a vector starting from the right antenna to the left antenna. Then we do this calculation. And after we determine that, so because we have the location of the center of the beetle, which is X, so the left antenna will be located in this position. XL is equal to X plus D0. D0 is the distance between the two antennas times direction. This is a directional vector divided by 2, and the right antenna location will be this one. And after that, what we do is we do the evaluation. We know at this moment, we know the location of the left antenna, the location of the right antenna, and then we measure what is the function value, which is F. The F left will be the value at the left antenna. F right will be the value at the right antenna. And what to move next step. This is the case step over here. Then we move using this update rule. So it is step times direction times, this is a sign function telling us whether the left antenna has a higher smell or the right antenna has a higher smell. And this one determines whether you move to the left antenna direction or to the right antenna direction. Well, the direction vector is defined by dir, which was originally a random variable. The movement step length is determined by this k parameter step. So we mainly have this full line of codes, but it is quite powerful. I will show you that in some simulation experiment, so that this is a really powerful algorithm. So the algorithm is very simple, as shown here. Note that this is only for a single beetle. You know, in biology and evolutionary computation, people usually think intelligence, human intelligence or animal intelligence, it might come from swarm behaviors. Just like a single cell may not have intelligence, but a group of cells composing together into a human body, and finally, or into human neural systems or human brain, we are able to get some intelligence. But this algorithm we proposed, which only rely on a single particle, a single beetle, it is a paradigm shift in the sense that a single cell, a single particle is also able to generate a kind of intelligent behavior. Well, we have some rules for the key parameters, like for the step length. For the step length, actually, as I will show you later in the simulation, you know, so that if you look at this algorithm, you may think that you may have two confusions. The first confusion is that whether it is possible to go to the maximum. Well, but basically, because this is inspired by the beetle behavior, the foraging behavior, you may have the feeling that it is possible to get to the optimum. But the second question you may have is that whether it is able to overcome the local maxima, whether it will be able to fall into local optima. Because, it seems like, okay, if the left side is having a higher value, I just turn left. If the right-hand side have a higher value, I just turn right. This simple behavior may generate the local optima. If that's possible for this algorithm to reach globally optimum, the answer is yes. The trick here is about the step length. Well, what we used for the step length over here is that originally we set the step length to be extremely big value, and we exponentially reduce this value. And it turns out, using this simple rule, we will be able to reach global optimization. The reason that it is possible to reach global optimization by using this very simple rule is inspired by the fact that if a human walking on the street by following this rule, it will be able to climb up like if I'm climbing a mountain, I'm using this way, and my step length is longer. Definitely, I will also fall into a local optima, but this local optima will be at a scale of the step length. Definitely, if there is a small peak on the ground, very small, maybe at a centimeter level, I will never fall into that kind of local optima because my walk step length is at a meter level, right? But if there is an ant on the ground, if it is walking, its step length, maybe it is at the millimeter level, it may fall into a local optima, which is like at a millimeter level. But in our rule, we originally set the step length to be very big, meaning that if there is a small peak on the function, which is at a scale shorter or smaller than the original step length, it will be filtered out. And so at the stage that the step length is quite big, so it will filter out some large scale local optima. And gradually we reduce the step length, and gradually we reduce the granularity. And finally, we are able to find the global optima. This is the basic ideas behind this kind of operation. As shown by this simple function, this function actually has multiple local optima. And we run our simple algorithm, and clearly that this is a global optima. After several steps using our step length rule, we are able to finally achieve the global optima. But again, like many other, almost all the evolutional computation algorithms, so this kind of convergence to the global optima is in probability, not deterministic. As shown by this simulation run, so there are also some local optima for this function. But again, using our algorithm, originally set the step length to be very big and gradually exponentially reduce the step length. And finally, we are able to reach the global optima. This is a sample MATLAB code for this algorithm. But basically, again, the key part of this algorithm is only full line of code. Therefore, you can implement this algorithm on any kind of programming platform, any kind of programming language. You can use a Python, Java, MATLAB, C++, whatever you want. Or even you can use assembly language if you want. Because some people, they want to implement the code in microcontrollers. But indeed, actually, we implemented this code on microcontroller. And also some researchers, they published their results using FPGA to run this algorithm, which is very crazy and very surprising. Because people usually have a concept that evolutional computation usually is quite computational burden is usually high. because you usually have multiple particles. And therefore, maybe you cannot run it for embedded systems. But here, the algorithm we propose, it's really simple, just a full line of codes. But it is really powerful in the sense that it can do global optimization, which gives the opportunity for, like nowadays we use Internet of Things, edge computing very much. Well, for those applications, probably one bottleneck is that because that is like for edge computing, you are usually consider run the systems on the edge in the sense that you don't run it on the cloud. Definitely, you cannot afford high computational cost algorithms. But for low computational algorithms, usually it is less powerful. But this algorithm, it is powerful, low cost, and low requirement for the computational power. And there are some case studies. Actually, if you search beetle antenna search, or its abbreviation BAS, you can find, you Google it, you can find a lot of resources and a lot of papers published in recent years on this topic. I just particularly list some representative studies on it. The first one is using this algorithm to optimize BP network so that it will not fall into local optima. So this is a sample algorithm published by others. And this is another example, like it is, for the gantry crane, if you drive it from position A to position B, usually after it reaches position B, it will swing for a while before it fully stop. But definitely that is dangerous. We expect that you can immediately stop at the location B by controlling the motion when you move it from point A to point B. Well, this is so in principle, this is a dynamical programming problem, but we can also partition into several time steps. And each time step, we maintain a constant control input. And then we can convert this problem as an optimization and but actually there are really many parameters. If you use traditional optimization, you have to have a lot of variables and you need to spend a lot of time. But actually you use our algorithm, you can quickly find the solution. This is the programs for it. And this is the time profile of the control input. And it can finally solve the problem. We also proved the convergence. Sorry that there are some Chinese characters here because we made two versions of the slides, and one is the Chinese version, the other one is our English version. But somehow today I was about to present for today's talk. I somehow cannot find my English version. Therefore, I quickly made some editing, but still didn't fully finish. Therefore, we have a part using Chinese characters. I apologize for that, but it does not matter. I can interpret a little bit about what's talking about. Basically, we published some papers proving that this algorithm is globally convergent to the global optima with the probability 1. Some people also explore the application of this beetle antenna search algorithm for the optimization of PID parameters, which has achieved the improved performance than its rival algorithms like genetic algorithm, PSO, and the Firefly algorithm. This is the application of this beetle antenna search algorithm for the navigation of drones for the path planning of drones. As you can find that this kind of environment is quite complex, but the beetle antenna search, there are two advantages in comparison which motivates the authors to use this algorithm in this kind of application. The first reason is that it is possible to do global optimization. In many industrial applications, we do really need a global optimization solver. The second reason that they really use this algorithm is that there are some global optimization solvers like genetic algorithm PSO, but computational burden is high. For drones or for other robotic systems, usually the computational power is not that high. They cannot afford high computational algorithms. They need low computational cost algorithm. Well, B2 antenna search is such kind of algorithm. Well, this is another application which use algorithm to control. This is a KUKA robotic arm, which has achieved very great results. This is another application. Use BAS, B2 antenna search, for the for the filtering of noise for fiber gyros. You know, for this kind of fiber gyro, it has been commonly used for planes, for drones, for missiles. But this is like a very small device. Again, usually this is the signal is processed by its embedded controllers. The embedded controller cannot run, for example, deep learning. Definitely, it is not possible. But they do really need some global optimization algorithms running on board to do the signal filtering. Well, therefore, they selected B2 antenna search and achieved a great result. This is the application of BAS for financial applications. This is for the investment optimization, portfolio optimization. It can tell you which combination, which investment strategy is the best in a real-time fashion. This is the BAS application for past planning. This is like, you know, this is a bearing. For bearing, there is like a developing domain, which is on the predictive maintenance, in the sense that, you know, there are some mechanical structures which has this kind of bearing. If you run long time, actually the bear may have some fault. Well, if you want to repair it, you have to fully stop all the systems, which result in a big cost of money. Well, therefore, they want to predict when this kind of thing will happen based on historical data. Well, here, they usually also run this kind of algorithm in their microcontrollers so that they can put this algorithm directly to the edge, to the terminal side. And also they expect the algorithm to be intelligent, to be able to do global optimization. Therefore, they use the B2 antenna search because they are able to model the problem as an optimization. Well, this is for the application of B2 antenna search in aerospace applications. Basically, this application is for performance seeking. By saying performance seeking is that they define a parameter. This parameter has dependency on some decision variables, but they do not exactly know what is the dependency. Mathematical model, they don't know, but they know exactly there are some deterministic dependency on the decision variables. They just are based on the real-time sensing of the performance index to tune the input parameters, to tune the decision parameters so that the performance index is maximized. There is also an active field which is called source extreme seeking, which used to be very famous research direction in Russia. And some other professors are also exploring this direction. that direction is also doing exactly the same thing that we do the real-time optimization, model-free optimization by directly mirroring the index. So here, they also tested the application of B2 antenna search for this application and achieved a good performance. The reason, again, that they use it because, B2 antenna search is low cost and low computationally low cost. Therefore, they can do it in real time in embedded controller. They can do the control in a very high control frequency. This is the application of B2 antenna search for power plant optimization, power grid optimization. This is for the optimization of 6-degree freedom torque and force sensor. This is for the thermal system management using BAS. Again, the reasons that so many applications they are using B2 antenna search for 2 reasons. The first reason, it is a global optimization for model-free problem. Second reason, computational cost is super low. It can run in embedded system. This is, as mentioned, that some people, they implemented this algorithm on FPGA so that speed can be even faster. And this is the screenshot from those published papers. And some people also extended B2 antenna search to multi-objective optimization. This is using this algorithm to find the Pareto front. This is using this modified algorithm to very high dimensional optimization problems. Actually, in this example, they tested the application to solve an optimization problem on a 10,000 dimensional space, 10,000, which is really big, but it is still quite powerful to find the optimization. As you can find, actually, this algorithm only cost 7 seconds to find the optimization solution, optimal solution for 10,000 dimensional space. This is for the battery management using the B2 antenna search. Again, because this algorithm is simple, can be simply deployed onto embedded systems. Therefore, they use it. This is for the image detection for the soldering. This is for the power system fault tolerance, fault diagonals. This is for the image enhancement. All of them are the applications of this algorithm. This is using the B2 antenna search for the optimization of wireless sensor networks. This is for these power storage system. They use a B2 antenna search algorithm. Again, why do they use this algorithm? 2 reasons. The first one, global optimization for model-free. Second, computationally low cost can be simply implemented on embedded computers. And therefore, this algorithm obtained a lot of application in industrial systems, not only the academia. This is for the optimization of the water. So some engineering problems on the hydrogen systems. This is for the unmanned surface vessel applications. This is for the application of B2 antenna search for the wear detection. And also because we proposed this algorithm 5 years ago, 5 or 4 years ago, after the proposal of this algorithm. On one side, on the theoretical part, many people are trying to incorporate new techniques to enhance the performance of this algorithm by proposing modified algorithms, its variants. The other research activity is that some engineers, they apply this algorithm to different engineering applications and achieve the great result. This is the modification of this original algorithm to use for the surface vessel applications are used in ocean engineering. This is another variant of this algorithm. This is so the kind of like mutation between beetle antenna search and the ADAM algorithm. We know that ADAM is a quite powerful algorithm in machine learning. And some researchers, they combine the two algorithms, integrate them together to develop some more powerful algorithms which can make beetle antenna search more powerful and more simple. And another application is that some people think, okay, for some applications, if you do not really worry about computational burden, they still can introduce a swarm of beetles. So as individual beetles still maintain the behaviors we developed based on the antennas. But additionally, you have some interaction between individuals so that you can develop more powerful beetle swarm optimization. This is the evaluation of the algorithm. This is another extension of the beetle antenna search to swarm applications, which is called the beetle colony optimization. So they introduce different interaction behaviors so that it has different strengths. They applied it to a tourist salesman problem, which is a typical combinatorial optimization problem, and achieved a great result. This is another application extension from a single beetle to multiple ones, which is called BAS-An. Well, they also used for different applications and achieved a good result. This is the application to a beetle antenna search to Q-learning, so that they can again achieve. It's kind of like they combine beetle antenna search with reinforcement learning, so that the system can learn by itself. This is using beetle antenna search together with the recurrent neural network to control robotic arms. Well, different, because in this application, one unique thing is that this application consider obstacles. If there is the presence of obstacles in the space, the path planning problem for a robotic arm is no longer convex. It is typically non-convex. Well, if you still use the convex solver, definitely it is less efficient, or even fail sometimes. Well, this paper, they take advantage of the global optimization power of beetle antenna search. And additionally, because this is controlling robotic arm, it is a time sequence. And therefore, they introduce a recurrent neural network and combine them together, achieved simultaneous path planning together, path tracking together with obstacle avoidance. As you can find that there is an obstacle, the robotic arm is able to keep track of the curve, and in the meanwhile, successfully avoid the obstacle for the whole body of the robot. We also tested the beetle antenna search algorithm over different benchmark test beds. So basically, there have been extensive applications of this algorithm and extensive extensions of this algorithm. If you are people working on the applications, if you are working on some engineering problems, either your problem can be modeled as a non-convex optimization, or your problem is you do not have a mathematical model, but you have the data. You can treat the system as a black box. even though you don't know what is inside the black box, but you know what is the input and what is the corresponding output, you can use B2 antenna search. Or if you are a practitioner in evolutionary computation, you can also try to extend your existing techniques to the B2 antenna search because it is relatively young and there are a lot of space to be enhanced for this algorithm because there are still not quite powerful, but this is a kind of advantage, meaning that there are still some space to be improved. There are some publications on this topic. We just summarized some like old publications, but actually in recent years, there are many more. All right, any question? Thank you.
Thank you very much, Professor Lee, for your interesting talk.
Thank you.
And now, dear colleagues who would like to ask a question.
May I ask a question?
Yes, please.
Okay, thank you very much for good presentation and very impressive results. I would like to ask the following questions. First one, this algorithm looks very simple. Can we apply any theoretical analysis about its convergence or maybe about how to control convergence speed and so on? I know that many approaches like genetic algorithm or differential evolution have a lot of steps, and many steps use a lot of randomness. That's why it's very hard to apply any theoretical analysis. But here we have very simple steps, like many methods from mathematical programming. Do you know any attempts about theoretical analysis?
You mean the theoretical analysis for the for what?
About convergence.
Convergence, yes.
Yes.
In the theoret, we also have a paper theoretically, which has already been published, which theoretically proved the global convergence to the global optima in probability 1. The basic idea is that, you know, we can construct a Markov chain because we also have some random mechanism, which finally, this Markov chain actually, the only at the global optima, this is the attraction state. For all the other states at different locations, they have a transition probability to transfer from the current location to the global optima. And until the moment that it has reached the global optima, it can never escape. This is a basic idea to prove the global convergence. But additionally, intuitively, you can look at this algorithm from a different perspective. You know, if you think, some people mentioned that you can understand this algorithm from this way. This is a beetle, right? There is a left antenna and a right antenna. If the right side has a stronger signal, like in this situation, because it is more close to the pizza, what it did is like move to the right. You can also think in this way. It is a random partition, it is a random tree in the sense that every time when I reach this location, I find right-hand side is has a higher strength. I just partition the space into two parts, left part and the right part. And I can conclude the pizza must locate to the right-hand side. And at each time when I do this evaluation, I just partition the space into two parts. And I can conclude where is the pizza, whether it is on the left side or the right-hand side. And then, based on this idea, you may be able to prove this kind of convergence could be exponentially fast in the sense that you cut the space every time you do a two-part partition. If you do 2 times, so the space will be partitioned into 4. If you do 3 times, the space will be partitioned into 8. This is exponentially reduce the size of the space. And finally, you will be able to inference where is the source locates. Yeah, I hope my answer, solved your question.
Yes, thank you very much. I think I need to get more information to become more,
how to
say,
maybe
to get in details.
Yeah. Can you write an email to me so that I can forward you that paper? Give the details on that. On the technical details for the proof.
Yes, thank you. Right now, it seems for me it looks like a stochastic gradient. So you try to understand in some random direction in a way, the way the function reduce its value.
I agree with you that there are some random mechanisms, stochastic mechanism, but there are also some deterministic mechanism. The deterministic mechanism actually ensures that it's greediness, so that it always go to the source in some way. Well, the randomness actually it is for like we ensure that it has some global performance. But another trick we played here is that, again, as mentioned, originally we set a step length to be really big, which can filter out some local optima. So if somehow, like if the step, actually the step length, we haven't proved this conclusion mathematically, but the idea is that we found that the step length could serve as a kind of filter. Just like in control, I'm having the control background. In control, we know that if your sampling rate is very low, your AD converter can serve as a kind of low pass filter. Here, the step length also can be used to serve as a kind of low pass filter. While the local optima, it's kind of like noise. If you use a low pass filter of a proper size of the length, the scale, you may be able to filter out those kind of noise to avoid this kind of like local optima. But gradually you reduce. And this is basically the trick. Even though there is some stochastic mechanism, but actually this stochastic mechanism does not harm the efficiency of this algorithm too much.
Yeah. Okay, let us give possibility to ask a question to somebody else.
Yes, thank you.
I have a question.
Yes, please.
So this is interesting approach, and as you probably heard my previous talk about competitions in evolutionary computation. So it would be interesting to see your approach in some of the competitions. Why did not you participate in optimization competitions?
Oh, I even don't know, because I traditionally not in this area. But yeah, today when you give the talk, it reminded me. I will definitely attend the competition next year, because traditionally I'm doing the control theoretical things, and I migrate into this field because I found that we can leverage some control tools for this optimization and even reach global optimization. Therefore, I'm relatively new in this area. But yeah, it is quite interesting for your talk. You mentioned like the CEC 2022 optimization competition, and I will definitely participate in this kind of contest and in the future.
Okay, great. Would be interesting to see.
Thank you very much.
Thank you.
Now it's time to make a break. Now we have break 20 minutes until 19:30, when our regular section will start. You are welcome to participate.
All right.